This lesson is about nonlinear systems of equations. To solve systems of nonlinear equations, the substitution method is generally the best choice. The elimination and Gauss-Jordan methods can be used, but you have to be very careful with like terms. Since nonlinear equations can intersect at many points, it is possible to have more than one solution to a system. It is a good idea to consider the types of graphs you are working with and estimate the number of solutions you could have before you begin. Let's look at some examples. In this example, I have x squared plus y squared equals 25 and negative 2x plus y equals 5. The first equation you should recognize as the equation of a circle. And the next equation is the equation of a line. If you think in your head the number of solutions we could expect, it's possible I could think of three different cases. We could have a situation where the line intersects the circle in two different points, and we would find two solutions. Or the line could intersect and actually just touch the circle at one point, and that would give us one solution. Or the line and the circle might not intersect at all, and there would be no solutions. So that's what we need to be thinking about in terms of when we get our answers, what to expect in terms of the number of solutions. As mentioned, the substitution method is generally the preferred method for solving. So I'm going to begin by choosing one of the equations and one variable to solve for and get it by itself, then substitute into the other equation. So for instance, I will start with the second equation and solve it for y. So that means y is equal to 2x plus 5, because all I did was move the negative 2x to the right-hand side of the equation. Now I can plug that into the next equation, x squared plus y squared equals 25, but I'm just going to substitute 2x plus 5 for my y. Next thing that I need to do is expand the 2x plus 5 quantity squared using FOIL. So I'll have x squared plus 4x squared plus 20x plus 25 equals 25. And now these parentheses aren't even necessary. They're simply indicating what I squared at this point, but there's no constant multiplier on the front of the parentheses, so they're not actually necessary. So the next stage in the process, I could subtract 25 from both sides, since I notice it will cancel out on both sides. And then I have x squared and 4x squared that can combine into 5x squared. So I have 5x squared plus 20x equals 0. Now, to continue solving this, I need to take a common factor of 5x out of this equation. So 5x times the quantity x plus 4 is equal to 0. And setting each one of these factors equal to 0, I have 5x equals 0 and x plus 4 equals 0. So that when I divide both sides by 5, I learn that x equals 0 will lead to a solution. And when I subtract 4 from both sides, I'll learn that x equals negative 4 will lead to a solution. Now, the thing that I want to be careful of is knowing that I could have as many as 2 different solutions to this system, I need to make sure I don't say that my solution is at the coordinate 0, -4. 0 is an x value, and -4 is an x value. Neither one of those is a y value. So this is not correct. That's why I wrote it in red. So what this means is I have two solutions. One of those solutions has an x value of 0. The other one has an x value of -4. So I need to determine what the y values are for each one of those. And I can go back to either one of my equations. The easiest one is going to be this linear y equals 2x plus 5. So let me come back down to where I was working. If x is equal to 0, and I'm using y equals 2x plus 5, then y is equal to 2 times 0 plus 5, which is 5. So one solution is the coordinate pair 0, 5. If x is equal to -4, then y is going to be 2 times -4 plus 5, which is -8 plus 5, or -3, which is the coordinate pair -4, -3. So these are my two solutions. Now, to verify this, let me draw this system for you and plot these points on that system so that you can see that these in fact are the intersection points of the system. Everything works the way that we would expect it to. I already have that drawn, but I have to scroll back up to see it, and here is that system. So because I can't hand sketch circles very well, I decided to go ahead and just have it pre-drawn by computer. Now, if you'll notice, there are two intersection points to this system. The first is located right here, and the coordinates of this is 0, 5, which matches up with one of the solutions that we came up with. The other intersection point is down here, and that intersection point has the coordinates -4, -3, the exact same coordinates of what we just learned by solving. The next example, I have x minus y equals -4, and x squared minus y equals -2. The first equation is a line, and the second equation is a parabola. I'm not going to sketch these as I did the last time, but you can mentally deduce that between a line and a parabola, we could have as many as two different solutions. So let's use substitution and solve for this solution or solutions, and then look graphically at what those appear like. So I'll start by solving the first equation for x. So all I would need to do is add y to both sides. So x equals y minus 4. Next, I will substitute into the second equation, replacing x with y minus 4. So it will be y minus 4 quantity squared minus y equals -2. And I need to FOIL the y minus 4 quantity squared, which will result in y squared minus 8y plus 16, then minus y equals -2. Those terms just come down. Since there's a squared term, it's a quadratic, which means I need to get everything on one side of the equation and have the problem set equal to 0. So I'll begin by leaving the y squared as is, but I have an 8y and a -y on the left-hand side of the equation, which can combine into -9y. Then the -2, I need to add 2 to both sides in order to bring it over. So this would be plus 18 equals 0. Now I have a polynomial that I can factor. So I'll set up two factors that are equal to 0. So y and y multiply to y squared. And 18, I could either use 9 and 2 or 6 and 3. But since I need to get things to add up to 9, I think I'll go with 6 and 3 and check that first. So 6 and 3 would multiply to positive 18 if they were both negative, and they would add to negative 9. So those are correct, which means I have the coordinate of one solution, its y value is 6, and the coordinate of the other solution, its y value is 3. What I need to do now is come up with the x coordinate for each one of these. And I can go back to any of my equations, but I think the easiest one will be the one that's already solved for x. So x is y minus 4. So if y is equal to 6 and x is y minus 4, then x is going to be 6 minus 4, which is 2. So that coordinate, that solution is 2, 6. Be careful not to write 6, 2, because we determined the y coordinate first was 6. Make sure you get the x and y in the proper position. The other solution, when y is equal to 3, I would have x equals 3 minus 4, or negative 1. So the other solution to this system is negative 1, 3. So I have two solutions, which is definitely a possibility when you have a line interacting with a parabola. And just so you can see it, I have that drawn. And again, I went ahead and let the calculator do it so that it was as accurate as possible. Between this line and this parabola, you can definitely see two intersection points. Here's one, and the coordinates of that point are at 2, 6, which was one of our solutions. The other intersection point is here. The coordinates of this point are negative 1. Just be careful, if you draw down, it looks like it would be negative 2, but look at the scale here. This is actually negative 1 on the y-axis. I'm sorry, it is negative 1 on the x-axis. Negative 1 and 3. And that was the other solution that we had, which matches up with our intuition of the problem. Here's another example. The first equation is a parabola, and also the second equation is a parabola as well. And the reason that I know that is there's only one variable that's squared in each equation, and that's going to affect the graph so that it has the shape of a parabola. So when two parabolas are intersecting, it's possible that there's two solutions. It's possible that there's no solutions. And it is possible, although it would be a little bit unlikely, that there would be one solution. Let's see what happens by solving through substitution. So I'm going to solve the first equation for y. That would give me y equals negative x squared, because I need to subtract the x squared over. When I substitute that into the next equation, I get x squared minus 4x minus negative x squared equals 0. The two negatives in a row can cancel each other out and make a positive. So x squared plus x squared results in 2x squared, then minus 4x equals 0. If I factor out the common factor of 2x from these two terms, that would leave me with 2x times the quantity x minus 2 equals 0. And each of those factors, if I set them to 0, I would have 2x equals 0 and x minus 2 equals 0. So that if I divide both sides by 2 in the first equation, the x-coordinate of one solution is 0. And if I add 2 to both sides in the other equation, the x-coordinate of the other solution is at positive 2. Now I need to get the y-coordinates associated with each one, and I'll just go back to this equation here. So y is negative x squared. In the case when x is 0, y would be negative 0 squared, which is still 0. So one solution is at the origin, 0, 0. In the other equation, when x is 2, y would be negative 2 squared, which would be negative 4. Be careful here, because if I had negative 2 in parentheses squared, that would be positive 4. But negative 2 without the parentheses, the square is only attached to the 2. So you're only squaring the 2 and then applying the negative afterward. So this is in fact a negative 4. So the solution here is 2, negative 4. And let's look at the graph and see what happens here. So here are my two parabolas, and they indeed are intersecting at 2 points. One point is clearly the origin, 0, 0. And that's what we discovered through solving. And the other point has the coordinates positive 2, negative 4, which is what we discovered for the other solution. In this next example, I have a line and a parabola. So let's take a look at what happens when we solve this. So I'm going to solve the top equation for y, which would give me y equals negative 2x minus 2. When I substitute that into the next equation, then I have negative 2x minus 2 plus 4x minus x squared equals 5. I've simply replaced the y with negative 2x minus 2. Looking for like terms to combine, and because I have a square in the problem, I'm going to try and get everything to one side of the equation and combined. So negative 2x and 4x, if I combine those, that's going to result in positive 2x, then negative 2 minus x squared, and if I subtract 5 over, so minus 5 equals 0, then negative 2 and negative 5 can combine. So let me write this as negative x squared plus 2x minus 7 equals 0. And when I go to solve this, I would first try and factor, but it's going to be easier to factor if my leading term coefficient is positive. And that's easy enough to make happen if I just divide both sides of the equation by negative 1, which would result in x squared minus 2x plus 7 equals 0. Now, if I try to factor, the only factors of 7 are 7 and 1. So 7 and 1, if they're both negative, they could add to negative 8, or positive 8 if they're both positive. If they differ in sign, I could either get negative 6 or positive 6. There's no way that I can get those factors to add up to negative 2. Which means I either need to rely on completing the square or the quadratic formula to continue solving this problem. My preference is the completing the square process, especially when that middle term, this negative 2, has a coefficient that is even. So to complete the square, I'll move the constant to the other side of the equation. And then I'll take the b term, which is the -2. I'll divide it by 2, which would result in -1, and then square that value. That gives me +1. So I'll add +1 to both sides. Next, x squared minus 2x plus 1 is a perfect square trinomial, which will factor into x minus 1 quantity squared. -7 plus 1 results in -6. So when I take the square root of both sides, I have x minus 1 is equal to the plus or minus square root of -6. And then I'm going to add 1 to the other side. So x equals 1 plus or minus the square root of a negative. You can only pull out the factor I and express it as I square root of 6. Now, what's happening here is I have two complex solutions. What that means is these graphs, they do not intersect in terms of the real numbers. And the xy plane that we look at visually is only for real numbers. So these don't intersect on the xy plane is basically what that's telling me. So because these solutions are complex, it tells me that there's no solutions to this system. There are no points of intersection. I don't need to go get the y values that are associated with these x values because they're not intersection points in the first place. However, if the homework asks you to provide the complex solutions just for practice, make sure to do that, but understand that this is a result that tells you that the graphs just don't intersect. And so that you can see it visually, here are the graphs of those two equations which do not intersect one another. So when you have linear systems and there are no solutions, you're going to end up solving and get a contradiction at some point where 5 equals -6 or something to that effect. That's a contradiction. When you have no solution to a system that's nonlinear, then you're going to end up with complex solutions. Here's one last example where y is equal to the natural log of x plus 1 and 5x plus y is equal to 4. In this example, no matter what we try, there's really no way algebraically to solve this problem. So for instance, if I tried to substitute the natural log of x plus 1 into the other equation, it would look like this. And then if I got the logarithm by itself, which would be our best guess as to how to solve this, I would have 4 minus 5x on the right-hand side of the equation. And then the natural thing to do at this point would be to raise both sides of the problem to an exponent because the argument of the logarithm has a variable. So it would be e to the 4 minus 5x power equals x plus 1. But now there's a variable in the exponent of my exponential equation, which can't be solved unless I switch it into a logarithm. So there's no way to do this algebraically. In this situation, what we need to do is to estimate it using the calculator. Because if you graph these on the calculator, you can definitely see that there is an intersection point. So I'm going to use y1 as the natural log of x plus 1. and y2 as y equals 4 minus 5x. I'll graph it in the standard viewing window. And visually, you can see that there is an intersection point, and there is only one intersection point, although the graph isn't completely accurate because the graph actually looks more like this right here, where if I bring up the natural log continues down to negative infinity. It approaches this vertical asymptote that would exist right here. So it continues down to negative infinity, but regardless, there still is only one intersection point. So the graph on the calculator isn't the most accurate graph we could get, but it does show that intersection point. In solving for that intersection point, one thing that you want to avoid is putting the cursor on screen over top that intersection and using that as your estimation. It will give you something close, but it will never be accurate enough. What you need to do is to allow the calculator to solve for it. So second and trace gets you into the calc menu. And that calc menu allows you to do calculations based off of graphs of functions. Option 5 is the intersection point between two graphs. If you select that, it'll bring you back to the graph window and ask you to input 3 items. The first item is what your first equation is, and it will default to y1 if you've only got 2 equations into your calculator. So the first curve is y1. I'll leave it that as is. The second curve, it defaults to y2 if you just have 2 equations in your calculator in the first place. So I'll leave that as is. Just press enter. Then it wants an initial guess. So it wants you to put the cursor as close to that intersection point as possible so that the intersection point that it calculates is as accurate as it can be. So the intersection point, I'll round to 3 decimal places, and let me state that this is the solution. It occurs at 0.695 and 0.527. That is the intersection point. The calculator gives you an estimate that's accurate to as many decimals as it can hold. Just follow the rounding rules that are given to you in your homework. Generally, they're asked for either 4 decimal places or 3 decimal places. But you need to make sure it's accurate to that many decimal places, or else it will mark it wrong. And if you look at the graph here, this is accurate because 0.695 is a good estimate as to where the x-coordinate is here, because at this point we're at 1. And 0.527, this dash mark would be 1, so this would be about 0.5. So 0.527, that does look accurate. So 0.695 and 0.527.